Okay. Hello, everybody. Welcome to chapter 19. Man, I don't know what happened, but this morning I woke up with like a really bad crick in my neck. I'm not sure why, but oof, really stiff. Anyway, we're going to start on chapter 19 talking about interference of light. And it's really fascinating, this whole thing, how you get interference of light and you get bright spots and dark spots and all this stuff. Um, and we're going to talk about double slit interference, thin film interference, and I'll just mention there is something like single slit interference as well. And we have a great demo I can do at the school with diffraction gratings, but we won't be able to do that. So let's just talk about interference. This lesson is just going to be on double slit interference. Okay, first of all, let's talk about the difference between coherent and incoherent light, which is pretty important. Coherent light is light that is one wavelength and all in phase. So in other words, you recall what we mean by in phase. They all start at the same part of the wavelength and they travel so that they are always, when there's a peak, there's a peak. When there's a trough, there's a trough. And so these waves are being generated. They're only one wavelength and they're all in phase. Incoherent light is made up of a bunch of different phases. So these are not in phase. Standard white light that you see is incoherent light. The book uses the analogy of if you drop a pebble onto a lake, then you can get nice smooth waves going out. Those are all in phase versus a bunch of rain falling around, creating a whole mess of waves and interfering with each other. And that's kind of the difference between coherent and incoherent light. Okay, so whoops, we got a stray coherent here. So if you have coherent light, if you recall back when we talked about superposition and interference of waves, if you have a crest on a crest, so there's one wave, here's another one, and a trough on a trough, you will get a much bigger peak and a much bigger trough. So in other words, you add up those amplitudes. On the other hand, if you get a peak and a trough, they will add up to nothing. So you'll get constructive interference in cases and destructive interference in cases. And if you recall, when you get constructive interference, you get these big amplitudes. For light, this is going to mean it's really bright. And when you get destructive interference for light, you'll cancel each other out and the amplitude will be zero. That will be dark. Okay, so this guy by the name of Young did this very famous experiment. He created coherent light, first of all, by passing light through a very, very narrow slit. And if you remember from Huygens' principle, only one set of waves would go through, and so he was able to create coherent light. Then he passed it through a double slit further on down the road. And I'm going to show you then what he saw on the screen. And you might be a little bit surprised by this. What he saw, first of all, was a bright spot right in the middle. And you think to yourself, whoa, how did that happen? We've got a barrier here. Well, if this screen is some length L away, and you've got a wave starting here at, we'll call this slit A and this slit B. Slit A to the middle of this screen back here, and slit B to the middle of the screen back here. This distance is going to be the same. They're both L away, and if you consider this the middle of the middle, and these slits are the same width, it doesn't look that way here, but they should be, you would see that these two waves are going to travel the same distance to get to here. They're traveling at the same speed, it's through the same media. So if this wave was at a peak here and this wave was a peak here, they're coherent, so they're going to be in phase, which means they're going to meet back here and they're going to be in phase, and you're going to get a really, really bright spot. Okay, that was interesting. Okay, let's pick another point. Let's say up here. Now, this wave B traveling from down here is going to travel this distance. And this wave here only has to travel that distance. They will travel a different distance. And here is the delta distance that they have to travel. If that difference in distance is 1/2 of a wavelength, can you see that this will still be a crest, say, and this guy, though, since it's half a wavelength behind, will be a trough. And so here you'll get a crest plus a trough, destructive interference, and it will be dark. Okay, let's pick another spot. I'm going to extend this up here now. And now let's go up to here. And now let's say the path difference is going to be, instead of half a wavelength, say the path difference is a full wavelength. Then you will get a crest plus a crest, and you'll get constructive interference, and you will get a bright spot. So what Young found was back here. If you take a look now at the screen, I'm going to turn this screen so that we are, let's say this is the horizontal. You'll get a bright spot in the central medium. Then you get this dark spot here, right? So this is bright, this is dark. This corresponds to this bright, and this is the dark here. And then you'll get another bright spot over here, and that corresponds to this bright. And these will be spaced out on both sides. You'll see that will happen on this side of the screen as well. And so you get this characteristic double slit interference pattern. And he was the first guy to point this out. And of course, this said light must behave like a wave. And so this intensity of the light is spread out, and this is at the 0 point. This here is the 1/2 of a wavelength. This here is a full wavelength, and this will repeat. You'll get bright, dark as you go further away from the central maximum. Okay, now let's say that there are two triangles here, and we're first going to look at say this guy up here, from the middle on up to here. We'll call this distance x. This distance between these two slits is d. There is one triangle in here. This is this little guy where we calculated the path difference. And then there is this bigger triangle from here, the center, back to here. Okay, I know this is getting kind of messy, and I wouldn't worry too much about the derivation. But as it turns out, this angle up here, we're going to call theta. That's the angle of this little triangle at the peak of the little triangle. And this angle here, as it turns out, is also theta, because those are similar triangles. Now, for small theta, this x over L, which is going to be opposite over adjacent, which would be the tangent, is going to approximately be equal to theta for small l's. This guy up here, sine theta, is going to be our path difference. Okay, so let's just call it lambda for now if we're talking one path difference, over d. So d is the separation between the slits. The path difference we're just going to call one wavelength for now. That is going to be opposite over hypotenuse, so that's the sine of that angle. But for small angles, it's also approximately equal to theta. So x over L, that ratio, is approximately equal to lambda over d. So if you solve this for lambda, you get d times x over L allows you to figure out the wavelength. If you measured these back here, you measured all that, that would let you know the wavelength. Or if you knew the wavelength and you knew your slit separation, you could figure out how far up the slit, the bright patterns would be. And this also can repeat itself, so there's a little integer you can put in here, and also you can have a half a wavelength for a dark spot versus a bright spot. But effectively what you'll end up with is this equation, which allows you to solve for wavelength for a double slit interference pattern. And that is on page 525 in the book. And there's also more descriptions of this experiment on page 525. So I'd encourage you to, 525, to go look at that. Double slit interference proves that light is a wave, and you need coherent light in order to get it, because that is all one wavelength and it's all in phase. So you can do the geometry of this little similar triangles here and solve for this equation. Okay, let's stop there, and we'll learn about thin films after this.